We've done a lot of focusing on just sigma bonds, but we all know that we have molecules that have more than just sigma bonds. So now we need to try to take a look at what happens when we have these pi bonds in molecules as well. What sorts of things occur and how are they significant? All right, so when we look at our sigma bonds on the bottom here, all right, sigma pi. Again, our sigma bonds are the first ones that form. We cannot have a molecule unless we have a sigma bond that forms between our atoms. So our sigma bonds are these direct end-to-end overlap. With our pi bonds, what we end up having are p orbitals that are half full. And those p orbitals, when they get up near each other, their orbital energy starts to overlap above and below the plane, and that's where we get our pi bonds forming. All right, so when we look at something with only sigma bonds, all right, something like ethane, everything has a single bond here. Okay, now this isn't quite ethane because I've got some green stuff on here. If this were ethane, everything would be a white ball with hydrogen. But I've got my single bond here, I've got single bonds, I've got single bonds. Okay, I've got nice free rotation around that bond there. And so I get this sp3 hybridization on both of my carbons. My sp3 hybrid orbitals overlap on both carbons, and then the other sp3 hybrid orbitals overlap with the 1s orbitals of my various different hydrogens. Everything's a sigma bond. All right, when I look at ethylene, all right, now I have a pi bond, okay? Now I've got this double bond here. And so remember that double bond is composed of one sigma bond and one pi bond. All right, and then these are sigmas. Okay, and so I get that direct end-to-end overlap that forms that sigma bond. That's this right here. And then the two p orbitals that are not hybridized start to overlap with each other, and we end up getting that pi bond character that forms. Okay, and so when we look at what's happening here, we have to account for what we're seeing. And so if I look at this, you know, I have my 2s and my 2p. Carbon has 1, 2, 3, 4. We get the mixing. So for this is trigonal planar. So we're only going to mix that right there. 1, 2, 3, we get our sp2, and then we have that 2p that's left over. I have 1, 2, 3. That accounts for each of the 3 sigma bonds that we see. And then that left over 2p. And so here, this accounts for the sigma bonds, and this allows for that pi bond formation. Okay? All right, same thing here. All right, we've got this formaldehyde, sp2 hybridization, sigma, 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 and then we have that one pi bond that forms with that oxygen. And so we have these 3 are sigma bonds, and this one right here is the one that participates with the pi bond. And so this is our sp2 hybridized carbon, all right? And then we've got that p orbital that didn't hybridize that gives us that right there. Okay, and so then we get something like acetylene, where now we have 2 pi bonds. So I've got sigma, and I have a sigma there, and then I have a pi bond and a pi bond. And so I have my 2s, 1, 2, 3, 2p for carbon, 1, 2, 3, 4. Okay, for something that's linear, I only need 2 things. So I'll pull these, we'll mix, and I have 2 sp orbitals and 2 unhybridized 2p orbitals. So 1, 2, 3, 4 electrons. And so this is where we get our sigma. And now I have the ability to do 2 pi bonds, which corresponds with my triple bond. Because remember, a triple bond is 1 sigma bond and then 2 pi bonds. Okay, so we're going to try drawing some of these. All right, we're going to look at a couple different molecules. First, we're going to look at carbon dioxide. And what's interesting is when we look at these two molecules, we're actually going to have to hybridize our surrounding atoms in order for everything to arrange the way it needs to see the type of geometry we see. So we'll draw Lewis structures, we'll draw orbital diagrams, and then we're going to sketch these orbitals to show where everything overlaps. So let's start with CO2. Okay, so for carbon dioxide, we get a Lewis structure. It looks like this. Okay, so carbon, we have 2 things. So we're going to get, what am I doing? Getting ahead of myself. Why do I keep writing the wrong thing? Sorry about that. So it's linear, which means we are sp hybridized. Okay? And then oxygen, well, we have this kind of thing going around. So this is a little bit interesting, right? Because technically speaking, that makes it very difficult because we only have 2 things hooked together, right? Just the carbon and the oxygen there. Oxygen is not actually a central atom. But I need to account for this sort of fixation. And so what happens with here is that no orbital mixing or hybridization leaves things in the wrong spot. Okay, and so if we didn't have this, then we wouldn't actually be able to get oxygen to form the sigma bond and the pi bond that's necessary. All right, so let's look at our orbital diagrams. All right, so carbon, we've got 2s and 2p, 1, 2, 3, 4. All right, we need to do our mixing. All right, we're going to get sp and 2p. 1, 2, 3, 4. Okay. And then oxygen, we're still going to get 2s, 2p. We'll mix. We're going to get 1, 2, 3, sp2, and then that 2p. So 1, 2, 3, 4, 5, 6. And so we have to account for everything. So here's what's going to happen. We have 2 lone pairs and a sigma bond, and then a pi bond. And so what we're going to see here, this is going to be a sigma bond. Sigma bond. This will give us spots for pi bond. Pi bond. And then these will be lone pairs. Okay? So we have to account for all of that. So now, how do we draw this? How are we going to represent all this? This is going to be a little bit crazy, but we actually do see this in order so that everything's in the right spot. Okay, so we have a carbon, an oxygen, and another oxygen. Okay. Wait, I don't mean to draw this. Okay, so we get that. We get that. And then we're going to get okay. So this is our sp2, our sp2, our sp2. Oh, no, not that one. Okay, our leftover 2p, our leftover 2p. All right, and then on carbon, this is our sp orbital or other sp orbital, and then we had 2p. So remember, unhybridized orbitals still have their 2 lobes, okay? All right, so that's one thing to keep in mind, that unhybridized p orbitals still have both lobes, because remember, a p orbital has 2 lobes to it, okay? And then here we have an sp2, 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 2p, and 2p, okay? So in our sp2s, on the oxygen, on the edges, there's all those lone pairs. So 2 lone pairs for each of them. All right, so there's our lone pairs. Now, in our sp2 overlap, there's where we get the bonding electrons for our sigma bonds. Okay, I need to erase this because I need some room. Okay, all right. And so what ends up happening? Now, this is kind of, it's a flat diagram, so it's a little bit odd to show. But basically what's happening is that in 3 dimensions, the way this is lined up, this 2p and this 2p overlap. This 2p and this 2p overlap. Okay, this 2p and this 2p overlap. This 2p and this 2p overlap. And in that overlap, we get our pi electrons. Okay? All right, so that's how we account for all of that. Now, when we look at HCN, same sort of a thing. We're going to do the whole shebang together. All right, so we get hydrogen, carbon, triple bond to nitrogen. Okay, so our carbon is in a linear fashion, so sp. Same thing with the nitrogen, because we have to have a place to show where everything arranges properly. Okay, so our carbon, we have our 2s and 1, 2, 3, 2p, 1, 2, 3, 4. We'll mix. So I get 2 sp and 2 leftover 2p. Okay, so I need a sigma bond and I need another sigma bond. I've got that triple bond, so I need 2 electrons that are capable of participating in pi bonds. Nitrogen, I have my 2s, 1, 2, 3, 2p, 1, 2, 3, 4, 5 valence electrons. We'll mix. Okay, I'll have my sp and my 1, 2, 2p. All right. So my nitrogen has a sigma bond, 2 pi bonds, and a lone pair. So that'll account for that. All right, and so we're going to get the same sort of a situation here. Sigma, sigma, pi, pi, lone pair. Okay. All right, you ready to try another one of those crazy diagrams? All right, so we've got our hydrogen, our carbon, and our nitrogen. Let's make the carbon a little more central. Okay. All right, so on the carbon, there's where we'll get that linear. There's our hydrogen. There's our nitrogen. Okay. All right, and then we've got two 2p orbitals that still have both their lobes on both of these guys. All right, and nitrogen was sp2 or sp, so we have that. Okay. All right, so this is the s orbital of hydrogen. This is an sp hybrid. This is an sp hybrid. Also an sp hybrid. Also an sp hybrid. Unhybridized 2p, each with 2 lobes. Okay. All right, so I'm going to get electrons there for a bond and electrons there for a bond. This is my sigma bond, or these are my sigma bonds. Okay, I have lone pairs left over here. Okay, and then we're going to get, let's see here. I can't draw. We're going to get overlap here. We're going to get overlap here. Again, 2 lobes means that they get overlap on the top and the bottom. Okay. And then for our pi bonds, it'll look like that. Okay? So we can take into account where everything goes with both orbital diagrams and these crazy overlapping diagrams here. Okay. Now, when we start looking at a single bond versus a double bond versus a triple bond, they get closer together the more you up the bond order. Okay, and so there's more electron density with a triple bond and it's closer together. There's less electron density with a single bond and it is further apart. One really important thing to consider with our sigma bonds and our pi bonds is if I have sigma bonds, I have free rotation around the bond. Okay, free rotation. This stuff can float around anywhere. But if I have that pi bond, okay, I can't twist it. I'm sterically hindered. There's no free rotation around that. And so that gives rise to what we call cis and trans isomers. All right, so this would be an example of a cis isomer. All right, this is an example of the one that's shown there. All right, and so these chlorines and hydrogens are fixed in place. The trans isomer, they're on opposite sides. So cis, they're on the same side. Trans, they're on the opposite side. Looks like that. And cis and trans isomerism has a lot of really important factors when it comes to whether or not things work right. So some stuff will synthesize and it will fall out in one isomer. Other times it'll fall out in a mixture of the 2 isomers. If we have a 50-50 mixture, we usually call that a racemic mixture. And this is very important because when we have different types of isomerization, we can get these cis and trans isomers, we can get optical isomers, all sorts of things that when we synthesize something, let's say it's some sort of medication, and there's an active site in the body. Well, you can see here with the cis and the trans, those are going to fit in different places. And so let's say you've got a spot in the body where the cis isomer fits, but the trans doesn't. And the cis isomer is your active compound. You want as much of that active compound in your medication as possible. Sometimes it's possible to separate these, sometimes it's not. Most of the time, the isomer that we don't want doesn't matter. Like something like Ritalin, the type of isomerization Ritalin exhibits is a racemic mixture. It synthesizes roughly in a 50-50. Sometimes it's like a 49-51, one way or the other. The other isomer of Ritalin does nothing. It absolutely doesn't matter that it's floating around there. But there used to be this like miracle weight loss drug that was called fen-phen. It synthesized in a racemic mixture. We could not separate it. And then people started dying. And what we found out was that, yeah, the active component, so good at weight loss. But the other isomer, it wasn't benign. It actually lodged in a different active site in the body and started killing people. And so they had to completely pull it because there was no way to safely ensure 100% separation of the two isomers. All right. Right here, you can see this cis and trans retinal. You can see where there's a change on that 11th and 12th carbon and where they would fit in different places. All right. And so, the type of bonds things have are very important with whether or not we get them to do what we want them to do. All right. So that looks at our valence bond theory and how it all ties in with our double bonds and our triple bonds. And so now we can account for more than just sigma bonds, but we can look at those pi bonds too.